Okay, when we left off, we were talking about transcription, and we were talking about transcription in bacteria, and we went through all of the parts of the promoter and the terminator, and the bacterial RNA polymerase, and now we're ready to look at transcription in eukaryotes. Now, you know how we are, right? We're pretty complicated. We're a lot more complicated than a little bacteria cell. And in eukaryotes, really, there are three RNA polymerases, not just one. Okay, so when we say RNA polymerase, most of the time we're talking about bacterial RNA polymerase. But if we're talking about eukaryotes, we can't just say RNA polymerase. We have to, we have to distinguish between them. Are we talking about RNA polymerase 1, RNA polymerase 2, or RNA polymerase 3? Okay, now both RNA polymerase 1 and 3 are used for tRNAs, rRNAs, and those little snRNAs that play a role in splicing. Okay, so that was 1 and 3. 1 and 3. Everybody got it? The odd numbers, 1 and 3. But RNA polymerase 2, that one is for mRNA. And that's the one that we've been thinking about the most. We're thinking about making an mRNA transcript to make us a little protein. Okay, RNA polymerase 2. Okay, RNA polymerase 2, it does differ slightly from the bacterial RNA polymerase. Okay, and it differs in two main ways. Number one, RNA polymerase 2, it doesn't have a sigma factor, right? Remember we said it kind of looks like Bart Simpson's butt, the sigma factor? Right. RNA polymerase 2, it doesn't have that. Instead, it's a lot more complicated. Instead, there are several, we call them general transcription factors. Okay, lots of different proteins that have to assemble onto the promoter before the RNA polymerase 2 can begin transcription, right? So all these proteins have to clump together, pile on top of each other, like a bunch of crazy football players or something. They all got to pile up in just the right order, and then RNA polymerase 2, will scratch its little molecular head and say, maybe I should go stick there, right? But it has to be all in the right order, and none of it works. Okay, so that's the first way that RNA polymerase 2 differs from bacterial RNA polymerase. The other way it differs, number 2, is that RNA polymerase 2 has to deal with nucleosomes. Don't forget that in eukaryotes, we have nucleosomes. Our DNA is packaged very well, very tightly packaged. Bacteria, they don't have to worry about that, right? So our DNA exists as chromatin. DNA, proteins stuck together. We got to worry about that. So our RNA polymerase 2 has to worry about that. Okay, so like I said, RNA polymerase 2, it doesn't have a sigma factor. Instead, it has to deal with these transcription factors or general transcription factors. Okay, and a lot of times they're called TF2s, transcription factor 2s. Can you guess why? Yeah, that's right. Because they go with RNA polymerase. Which one? Is it 1? Is it 1? No. Is it 3? 3? Huh? No. They go with 2. So the TF2s go with RNA polymerase 2, right? And they've got a bunch of different names like TF2A, TF2B, and so on, okay? And we're not going to worry about them so much. We'll just worry about a few of them just to get us started so you'll get the basic idea. Okay, so let's start with the initiation of transcription. It all starts off with one of those general transcription factors, TF2D, right? And it binds to the Tata box, okay? And in eukaryotes, it's about 25 base pairs upstream, as opposed to like the negative 30 upstream in bacteria. But, anyway, it's pretty much in the same place, right? And the way that TF2 sticks to the Tata box is because it contains a Tata binding protein. This is a special protein that allows it to stick to the double helix of the DNA and, create this huge distortion in the DNA and start to open it up a little bit, right? And then, there are a bunch of other proteins. As I said, we're not going to worry about that much. I'll just kind of quickly mention them. TF2A and then TF2B, they bind to TF2D. And then there's this TF2F and a bunch of other factors that stick to the RNA polymerase 2, and then TF2E and TF2H, they stick to the promoter with the RNA polymerase 2. Now, TF2H, we need to pay attention to this one because TF2H has a DNA helicase in it, right? You guys remember DNA helicase from DNA replication? The DNA helicase starts to open up. That's right, to open up that start site where we're going to start transcription, okay? But at this point, the RNA polymerase II, it's stuck to the promoter, and it's going to remain at the promoter. And then it's going to slowly synthesize a short length of the RNA, at which point it's going to undergo a conformational change. Okay? Now, this TF2H, this little guy is actually pretty important because TF2H also contains a protein kinase. Do you guys remember what a kinase is? Do you? Seriously? I hope so. Right? Can you tell me? A kinase. What does it do? It phosphorylates things. What does that mean? Phosphorylate. It means that it adds an inorganic phosphate to something, right? Or it'll take a phosphate from an ATP and stick it on something. Phosphates, they're negatively charged. So when you stick phosphates on things, things kind of shift around a little bit, right? And it causes conformational changes in things, in DNA and proteins and so on, right? Well, anyway, TF2H, it contains a protein kinase. So it is like not just a protein that sticks to DNA, it's an enzyme too, right? And what it does is it repeatedly, over and over and over and over again, phosphorylates the tail of the RNA polymerase II. Remember how RNA polymerase II has this tail that sticks up like a crooked cat's tail, right? Anyway, when that tail gets phosphorylated, bam, it switches gear, right? And then the RNA polymerase II will disengage from that huge collection, that big pile of all of those general transcription factors, the TF2A, the TF2B, the TF2D, the blah, 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 yada, yada, yada. It'll just disengage from all of those. And then the RNA polymerase II is going to be so anchored tightly to the DNA that it's going to kick itself into cruise, and it's going to go into an elongation mode. Okay? Now, there's one other thing that we need to talk about in terms of this. And that is the RNA polymerase II. Yeah, it also needs some other things, not just these general transcription factors. It's also going to require an activator and a mediator and some of those chromatin modifying proteins. Because remember, it has to deal with those little nucleosomes, right? We're talking chromatin. It's packaged. We got to unpackage it if we're going to transcribe it, right? So again, we need activators, mediators, and chromatin modifying proteins. Okay, so transcriptional activators, they bind to specific sequences in the DNA, and they help attract the RNA polymerase II, right? And the activator doesn't actually stick in the promoter. It sticks to what's called an enhancer region, right? Imagine that, right? All of your promoters get to be enhanced in some special way, right? But the activator, it can't just stick to an enhancer. It requires a mediator, right? Sometimes in life, we all require a mediator, someone to sort of get in the middle of it and go between, right? Okay, so the mediator sticks to the activator, and that lets the activator stick to the enhancer, right? And then, this way, the transcriptional activators can communicate properly with the RNA polymerase II and with all of those other transcription factors. Okay, now, the transcription initiation also requires this local recruitment of several of these chromatin modifying enzymes, like chromatin remodeling complexes or those histone acetylases. What was that? What'd I say? Histone acetylase? What's a histone acetylase? Come on, don't tell me you forget what a histone acetylase is. All right, let's back up a minute. Can you tell me what's a histone? Come on, you remember a nucleosome? You remember how nucleosomes are made up of 8 histone proteins, and each one of these histone proteins has a tiny little tail on the end? Yep, that's right. And you remember how those tails are positively charged because they contain all this lysine and arginine? Well, you remember how DNA is negatively charged because the backbone is made of a bunch of phosphate groups that are all negatives and positives? Oh, they love each other. They're attracted to each other, right? Negatives and positives, right? So the tails of these little histones, they suck right onto the backbone of the DNA, and they're not coming off, right? Okay, I'm sure everybody remembers that, right? Do you remember what an acetyl group is? Come on. Don't tell me you forget what an acetyl group is, right? A carbon double bonded to an oxygen with a methyl group on the end. A CH3 methyl group, carbon double bonded to oxygen with the methyl group, right? Ask yourself, shake your head, think. Does a methyl group have a positive charge? Nope. Does a carbon double bonded to an oxygen have a positive charge? Nope. Okay, so if you hook an acetyl group, carbon double bonded to an oxygen with a methyl group, if you hook an acetyl group onto a histone, does it still have a positive charge? Nope. That's right. Instead, you mask all of the positive charge on those little histone tails, and now the histone's not going to want to stick to the DNA, to the negatively charged DNA. Where's the love, people? It's gone. It's gone. And now the DNA, it doesn't love these nucleosomes so more. So what does it do? It does what always happens. It just walks away. It just walks away, right? That's right. Shed a little molecular tear for the situation. The DNA, it lets go. Sometimes it's the best thing you can do is to just let go, right? Just let it go. So then the DNA, it just starts to unravel. It's not going to hold on so tight to those little nucleosomes anymore because it doesn't love them anymore. There's nothing to love. There's no positive charge. There's no electrostatic chemistry involved anymore, right? So these histone acetylases, they're the ones that do this. They add this acetyl group and they cause it to let go, right? So now the DNA starts to unravel. It starts to become more spaghetti-like. I love spaghetti. Anyway, it becomes more spaghetti-like. And when it becomes more spaghetti-like, then the RNA polymerase 2, that's right, we're talking about RNA polymerase 2. RNA polymerase 2 can then run along the DNA and transcribe it and make our little RNA polymerase, or RNA transcript. Make that little tiny worm of an RNA transcript. Okay, well, I don't know about you, but all this talk about love has made me a little bit excited about the biological world, so I think we should take a quick break, and then we'll be right back.